All right, you fellow astronauts. See what I did there? It's like astronaut, but you're a nut. I'm a nut too. So, my fellow astronauts, welcome to the concept of telescopes. Now, right now, I'm going to say, you're going to be like, oh my gosh, did I have a printing error? There's no questions here. No, all the questions, I mean, we have a whole lab based on this, so there's no questions in this part of the workbook. So I'm just going to go over some of the more difficult concepts and some of the more difficult diagrams, which is where I'm trying to focus my energy in these workbooks and the stuff that it was my experience both with students and as a student that when you looked at these diagrams the first time, you were like, what the heck are they saying? So let's get into this diagram for telescopes. So this first diagram here is this diagram over here. Okay. And it's going into what is how telescopes work. Okay. So the basic idea here, okay, for how telescopes and even microscopes, because they both work on this principle of these convex lenses, is very similar idea. There's a little different. There's differences in like the focal length and all that kind of stuff is the only difference. They basically the same. Is this idea right here. So this is light approaches glass at an angle. So this is figure 6.2 in your book. Now, what the heck is going? It looks like a parallelogram that's been shaded with funny lines. What are they trying to say here? What these lines actually represent, and I'll turn the page to help you visualize this better, is that this is waves like this. So like the lights are supposed to be the peak part of the wave and the dark parts are the low part of the wave. So what they're really doing in this diagram is they're turning that line, what we usually think of as a line, into something that it's more nearly truly like, and that's like a folded surface. Now it's not even really like a folded surface like this because it's actually influenced in 3 dimensions. But this gives us a little bit better visualization if it were properly explained in the book, which it's not. It does not clarify this. I think they assume that you're better at math than most people coming into this are, that you've seen this when, why would you? This is a very introductory class. So that's what these lines represent. They represent these, if you looked at it, the size, like imagine a paper that's kind of wrinkled up. Now it enters this surface over here, and you don't have to shade this, but I'm going to go ahead and I'm going to shade this because this is our glass surface right here. And this is one, usually you do what I do, but I'm just shading it so that it comes up a little better on the camera right here. So this blue section here is glass. What happens when that light approaches glass? Now we learned that light has a maximum speed of what? Right, 300,000 kilometers per second. Okay, so this is the speed of light. But in a vacuum. In other words, this is the fastest light can go. This is the speed of light in a vacuum. Fastest light can go. But light can be slowed down. So this is really the speed limit of the universe, including light. So light can go up to this speed, but not break this speed. So light bends as it enters a piece of glass because what ends up happening is that the light is slowing down as it enters the glass. The glass is more dense than the air. Now, what's this bending called? Okay, we have the light coming in this direction. It hits that angled surface, and now it's at a slightly different angle. What is this called? Right, this is right here. This is called refraction. So that's what this image is trying to get into your head. And refraction happens in all sorts of different environments. This is one really cool one. This is the sun sometimes appears distorted because of how the light bends. And you can see a good image of that. So this at sunset, because this lower portion, it's passing through more of the atmosphere. Also due to temperature is another aspect as we get lower to the surface. But it's basically through more and denser material. It's causing a bend and it's causing the sun to kind of look a little bit like a squished egg. This is also what's going on in mirages, is that we have a difference in this density going through here, okay? And the different density in the air causes a mirage. So different densities of air cause refraction and mirages. So this is what causes a mirage. This is actually, this one in particular is called an inferior mirage. That's the one we're used to on the road. I recently got to see on Lake Ontario a superior mirage, which is very cool because it looks like things on the lake are floating above the lake rather than the things in the sky looking like it's actually on the land, causing kind of like a watery image. You're not really seeing water. What you're seeing is an inferior, you're not really seeing water. What you're seeing is basically like the color of the sky in the ground because of the bent light due to refraction. Now this is another super hella confusing diagram in your book. What's your book showing here? So if an object, we talked about this way back when we talked about the seasons, right? The sun is far enough away where the sun's rays arrive parallel to one another. And this is true of any very far away object. Any very, very, very far away object so for example, the sun, stars are so far away that the rays of light from the object arrive parallel. Not my best planning for note taking, but oh well, it's not the neatest in the world, but that's okay. So it's not just any object over here. It's got to be, for example, the sun or stars, but not your cat. Your cat is too close to you. Sun or stars are far enough away where the light's rays from those objects arrive parallel. So that's why these objects appear as disks or points. The light's rays are arriving parallel and are bent to a point. If you have purpose in your eye, it happens if you have perfect vision. I do not. But if I did, it would appear that way. So instead I get nice fuzzy stars. If I take my glasses off, let's be real, I see fuzzy everything, but I'm blind as a bat. So following each one of these, so for example, I'm just going to go use a couple of different colors, pink, purple, blue, and green in no particular order. Okay, just to see how the lines follow. This line, this top line gets bent like this. And I'll do it this way. That blue, the middle one will be green. This one passes, because it's not hitting at an angle, this is where that curvature, it basically, at the perfect part of the curve in the center of that convex lens, it's not going to be hitting at an angle, so it passes straight through. And then this bottom one down here hits at this angle. Notice it's a mirror reflection of that angle, bends up, becomes focused on that point. Now it's a little bit more obvious for closer objects. So for example, your dog is a closer object. These are very far objects. So for close objects, they do not produce a point, they produce an image, and that image is upside down. Now you might be like, Dr. E, that's nuts. I do not see things upside down. If you looked inside your brain, you would see that you are actually registering these things actually upside down, your brain right sides up, everything all the time. So these are two very close objects. Let's see how this gets bent, why the image ends up upside down. So the middle one that passes through that smooth part of the lens, that is, I'm going to keep that green, and that's going to pass right through like that. It's still going to be the same for both of these, both for your convex lens and the convex lens of your eye. So that's same for same. But now the top one, it gets bent, and because of the distance, okay, here you end up at a focus. Here you end up along a focal plane. It bends it far enough down where the object ends up with this point of light coming down here. Same thing over here. This point of light gets bent down there. Same too for this bottom ray of light. This bottom ray of light goes like this, and it gets bent, and it goes up here. Bottom ray of light gets bent, and it goes up here. Now it's a little bit more complicated than that because there's actually diffuse. So you have multiple, the light's rays are not arriving parallel, they're actually radiating from points. And those are going to hit at a variety of different angles. I just focused on the rays that are parallel from each other, but I don't want you to realize that this is a simplification. In the Buddhist metaphor, these are fingers pointing at the moon, not the moon. That's really deep, deep what's going on. But just to have an idea of why the object shows up upside down along the focal plane. Once again, this is very introductory astronomy course, just meant to give you a real basic idea. So if you were interested in pursuing astronomy further, you have the tools to do that. Or if you want to get your science credit because you're a criminal justice major or an accountant, you can do that too. So the focal plane is where light comes in from different directions to comes into focus, and the image behind that lens is upside down. Those are two important key ideas here for understanding how telescopes work. Now, two important properties of telescopes that determine basically how powerful your telescope is, and it shouldn't be 1 and 1, it should be 1 and 2, but oh well, are the light collecting area. Telescopes with larger light collecting areas can gather a greater amount of light in a shorter amount of time. So that's light is the information we're using to determine our stars or whatever we're looking at. So we want a larger light collecting area. And then angular resolution. So that's telescopes that are larger are capable of taking images with greater detail. So a telescope's diameter can tell us its light collecting area, but it's important to realize that it's not linear. So you don't say that a 10 centimeter diameter light collecting area is only half as good as a 20. It goes up by the square. Remember that cross-sectional area is equal to pi diameter divided by 2, and that whole thing squared, where that is equal to the radius. In other words, about equal to 3.14 times that diameter divided by 2 squared. Now, is this a super essential formula right here? Not at the moment right here, but it is pretty useful for understanding exactly how telescopes work, and that understanding that it's the quality of this, or the potential information you can be getting in your telescope is going up by the square as that diameter increases. So the largest optical telescopes, in other words, the largest traditional, you use your eye to see in them telescopes, have a diameter of about 10 meters, which is enormous. That's approximately equal to 30 feet, which is about a third of a football field, as far as I understand. I know that's 30 feet. I'm not so sure about football fields. So, quick discussion. How does the collecting area of a 10-meter telescope compare to that with a 2-meter telescope? I'll give you a moment to think about it. How would you set that up? So if you set it up like this, we could say approximate it, say 10 meter. So it's a 5-meter radius. So you have it to be about equal to 3 times 5 squared. In other words, a 75 meters squared. Okay. Versus a 2-meter telescope would be 2 meters divided by 2, which is equal to 1 meter radius. Because remember this in here, this right here is our radius. So that's about equal to 3. This is my approximation of pi times 1 squared is equal to 3 times 1 squared. 1 squared is 1 times 3 is 3 meters. So it is 25 times the light collecting area. Now, the fast and easy way, if you're good at math, is to just say, well, I can take 10 divided by 2 and square that. That's 5 squared, which is 25, so it's 25 times better. But this kind of walks you through, okay? This is about equal. I'm going to say about equal 3.14. 14 is what I really mean here, okay? So it's about equal to that. Now let's talk about angular resolution. So we have a couple of definitions that we've worked through already here. Cross-sectional area, light collecting area, and now angular resolution. So, to understand the angular resolution, it's useful to understand the angular separation, okay, which is what here. Now, I know I have aliens all over everything. I do want to clarify, I don't really think these kinds of aliens exist. Is it extremely likely in my mind that very simple life forms exist somewhere in the universe? Yes. Most of Earth's history was single-celled organisms starting to about 3.5 billion years ago. So we had about 3 billion years. In other words, the majority of Earth's history was single-celled life forms. So I think it's pretty likely there's single-celled life forms out there, even possibly elsewhere in our own solar system. Do I really think there's aliens like this? No, I do not. Do I think aliens like this are hilarious? Yes, I do. And that's why you see them everywhere. So, just clarifying that. So let's take a look at these two aliens and get an idea of what we mean when we talk about angular separation. So let's go ahead and put our friend Elliot, our observer. Oh, I can spell Elliot. Who says I can't? And see what the angular separation for the top and bottom of looking at this alien versus looking at that alien. So I'm going to start over here with this alien. This is one of the times to bring out your colored pens might be useful. So here's my angular separation if I'm looking at the whole image of this alien right here. It's like that. Whereas for this alien way over here, your book has the same image for a car. I think that this is much more fun than a car. It's an alien. And we can see that this is a much bigger angle. In other words, angular separation. Whereas this one over here, this is a very little angle or a much smaller angle. So angular resolution basically means or connects back to the minimum angular separation that the telescope. So these are the differences in angular separation, what we're looking at right here. So this tells you, can you see objects at a distance? If the object is smaller or farther away, there's going to be a smaller angular separation right there from the top or the bottom for that field of view. So you've already heard a little bit about the difference between refracting and reflecting telescopes in your lab. Refracting telescopes focus light with lenses, whereas reflecting telescopes focus light with mirrors. And most telescopes used for applications um, in astronomy for professional astronomers uses reflecting rather than refracting. And the reason for that is not anything special about the mirrors or anything, but it has to do with the technological and the engineering challenges associated with refracting telescopes. Whereas refracting telescopes have to have a very precisely like created lens that's precise on both sides and very high quality glass. A reflecting telescope, you just need to have a very good shape to the reflecting surface. So that limits the engineering problems associated with a reflecting telescope. Also, there are other factors like mounting the lenses, where it's much easier to mount a smaller mirror rather than a heavy piece of refracting glass in these large telescopes. Now, something that a lot of students ask me, what kind of telescope do I need to get for this class? So first, you don't need any telescope. But if you are going to get something to help you see anything, I would not recommend a telescope. I would recommend you should have binoculars. Why? Binoculars will get you really far. They're much cheaper and much easier to use than either a refracting or a reflecting telescope. Much easier to use. It's much easier to find objects. It's more portable. You can have it in your car, and if it's a pretty night out, just pop out with the binoculars. But high quality binoculars, it doesn't have to be super high quality. I mean, you can spend 30, $60 and still see a hell of a lot more than Galileo, which means you can see the moons of Jupiter. So you should be getting a pair of binoculars and not worry. Now, some people here are like really good hobbyists and they've already got a reflecting telescope and all that kind of stuff, and that's great. But if you're just starting out, binoculars are the way to go.